Recently, our client Tommy met his banker to discuss continuing his father's restaurant legacy. In us, he found a partner that understood the importance of passing the torch. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy. A client met his banker to discuss opening a restaurant in a busy airport. In us, he found a partner that understood the importance of reaching for the sky. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Mac.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on the Space Nuts podcast. This is episode 237. Good grief. I can't even count that high. Wow, 237. My name is Andrew Dunkley, your host, and with me, as always, is the good Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How is it going?
Oh, very well. Feeling very refreshed. Judy and I went on a little boat trip last week. Not a cruiser, not a cruise line. No, we didn't do that. We hired a houseboat and spent 4 or 5 days on the Murray River in southern New South Wales. Now, for those who aren't familiar with Australian geography, the Murray River runs east to west, and then it turns south and empties into the Great Southern Ocean. But it is a fabulous and famous waterway in Australia where people go to play, and it is a haven for people who like water skiing and wakeboarding. We did none of that. We hired a houseboat and just relaxed, trundled around for a few days. Never driven a houseboat before in my life. It's very easy. The hardest part to get used to, Fred, is when you turn the wheel, you've got to wait 5 seconds for the boat to actually respond. So you've got to, it takes some getting used to. The hardest part's parking, because this was designed to be sort of slightly run aground and then you tie it off to trees. But I had to get off to tie it to the trees. So Judy had to actually steer it to keep it straight because the water flow keeps wanting to push it downstream. So you've got to work the motor so that the boat stays at right angles to the bank. And yeah, the downside is we were right near that beautiful village of Echuca, which has got a wonderful paddleboat history where they used to take goods up and down the river before road and rail transport came along. And we couldn't go there because of COVID-19. The borders were closed and they reopened the day after we left. So that was really unlucky. But the border control there was just crazy. We went into town one day and it took us half an hour just to get into town because of the traffic. Trying to get across the border was just crazy. But wonderful, wonderful trip. Highly recommend it. Just the two of us on this boat. There were lots of other houseboats that housed a lot more people, but we got a small one. But it had a bedroom, an ensuite. It had an upstairs barbecue area, which was where we did most of our cooking. It had a kitchen, a dining area, and a living room. Beautifully appointed. Really, really, really good fun. And it's it was christened the Houseboat for Two. That's the name of the ship, Houseboat for Two, which is run by a couple of people who own a farm there. And yeah, really, really enjoyed ourselves. Fantastic fun. Now, Fred, we are going to be talking today about some new exoplanets. These ones have been discovered and proven to be a bit of a mystery. They have unusual orbits, but it could be a good thing because we might learn something from these particular planets. And SLABS. We're going to talk about SLABS today, not the ones that you put on graves or anything like that. SLABS are stupendously large black holes. That's what they are, and they've been discovered recently. We'll talk about those, and that dovetails well into a question from young Ashlyn, 9 years old, from Atlanta, Georgia, who is asking about supermassive black holes. So, Ashlyn, we're going to answer your question today, and Jarrod from Melbourne, following up something we talked about recently in terms of the 100th anniversary of E equals MC squared, which we did a while back, but he's got some pretty interesting questions for us today, which we will try and tackle. But first, let's talk about these exoplanets that have been discovered. What's so unusual about them, Fred?
They were a puzzle, actually, from sort of from the word go. But the unusual thing, and I'll say it now, but we'll talk about it in detail, is the resonances between these planets, where one planet orbits in an integral number of orbits of the other planet, if I can put it that way. The story, though, goes back quite a long way. This is an object that's been observed for quite a long time. The star is called TOI-178, and TOI is target of interest, which I think is a Kepler designation from the Kepler spacecraft. This object is about 200 light years away. So what we've got here is a star that has revealed the presence of planets by the fact that the light of the star dims as the planets pass in front of it or transit. And originally, astronomers thought that what they were seeing were two planets which actually were in the same orbit. In other words, one following the other around. But then a closer analysis shows that actually it's not two planets orbiting the star at the same distance, but a lot of planets, and in fact there are 6 now that are known, which are performing this kind of resonant dance where the orbits are interconnected. There's this work, I should say, has come from the Université de Genève in Switzerland and the University of Bern. Both have strong astronomy groups, actually, both of them. Okay, what's the situation? Well, you can look at it, in terms of what's happening in our own solar system. There are many resonances in our solar system. The best known is 3 of Jupiter's moons, Io, Europa, and Ganymede, which have this 4:2:1 ratio in the time that it takes them to go around. So Europa goes round twice in 4 orbits of Io, and Ganymede goes round once in 4 orbits of Io, and that means it goes round once in 2 orbits of Europa. So it's a 4:2:1 resonance. The other good well-known one is Pluto, which is in a resonant orbit with Neptune. So Pluto goes around twice for every 3 orbits of Neptune. And what's happened is that as these things have orbited over, the billions of years since the formation of the solar system, the gravitational forces have conspired to pull them into this sort of orbital resonance situation. What's happened now, though, is TOI-178 has been carefully observed. So it too has a resonant chain, as it's called. You call it a resonance chain. And it's 18:9 to 6 to 4 to 3. That's the ratio of 5 of the 6 planets. So let me just read the story. While the second planet from the star completes 18 orbits, the third completes 9 orbits, the fourth completes 6 orbits, the fifth completes 4 orbits, and the sixth completes 3 orbits. That's the 18:9 to 6 to 4 to 3 resonance chain. The innermost one actually doesn't follow that, that mathematical curiosity, I guess you might call it. But it's, as you've just said, the reason why this is valuable is it sort of tells you about the way these planets have orbited, have evolved, how the system has evolved since the birth of the star. And it suggests that the evolution has been what one of the astronomers describes as gentle. This is Jan Alibert from the University of Bern. He says the orbits in this, actually, I think it's a he. The orbits in this system are very well ordered, which tells us that this system has evolved quite gently since its birth, rather than, and as they go on to say, for example, by a giant impact stirring things up. It's a configuration that wouldn't have survived that. But there is one peculiarity about it, Andrew, which I'm sure you're about to mention. and that is these stars are all very different. They're, in fact, Nathan Hara, another, I think I remember working with him years ago, again at the Université de Genève, he says that even if the arrangement of the orbits is neat and well ordered, the densities of the planets are much more disorderly. He says it looks as though there's a planet as dense as the Earth right next to a very fluffy planet with half the density of Neptune, followed by a planet with the density of Neptune. It is not what we are used to, because in our solar system, we've got this nice arrangement of the four inner planets, which are all rocky and dense, close to the sun, and the low density gas planets are further out. They're all further out than the rocky planets. So there's a really nice quote again from one of the astronomers. This contrast between the rhythmic harmony of the orbital motion and the disorderly densities certainly challenges our understanding of the formation and evolution of planetary systems, because if they've had this kind of gentle evolution, you'd expect it would have turned out like it is in the solar system, with one type of planets in the inner part of that solar system and the other type well out. But no, they're all mixed up. And I might just mention, since I'm always glad to get a plug-in for this organisation, several telescopes were involved with this work, but in particular the very large telescope of the European Southern Observatory, ESO, with which Australia has a 10-year strategic partnership. So ESO is very close to our mind here in the world of astronomy in Australia.
Fantastic. So, as you mentioned, we can learn a lot from this discovery. What I wonder about is, we take for granted that the rocky planets are close into the sun and the gas planets are out wider, but there have been exoplanets discovered where there are huge gas giants very close to their parent star. So we are not, I suppose, typical. Or
no, that's right.
Have they discovered that is more typical than other scenarios, or it could just be anything?
One of the reasons why, and the things you're talking about, the gas giants right next to their stars, they're called hot Jupiters. And we've found a lot of those, and one reason for that is probably that they're the easiest to find. Of all the planets going around other stars, they're actually the easiest ones. The signal, the information that they present is very much the information that's most readily detected. So, but you're also right that there are things about our solar system that we don't understand, and there's all the people who look at the history of orbits in the solar system, and you can do that by running the clock backwards, suggest that the gas giants in particular have moved around quite a lot, migrating inwards and outwards in the solar system, probably not within the central zone where the rocky planets are, but but certainly in and out. And in fact, one piece of research suggests that maybe Neptune and Uranus actually reversed position at some point. So, these are really interesting features of our solar system. But still, the scientists who work on this kind of thing will learn a lot from the famous exoplanet system TOI-178, which I think has still got many secrets to reveal.
Yes, it has. And I suppose there are probably systems we've discovered where we're looking at gas giants, but there might be rocky planets in there that we haven't found yet, or there may not be a standard model for how solar systems form, and ours obviously formed in a more dramatic fashion than this one we're talking about, which seems to have just sort of become a more cooperative type of gathering of planets in a beautiful dance.
Yes, that's right.
Perhaps.
Exactly. It's lovely stuff.
It is indeed. You're listening to the Space Nuts podcast. Good to have your company. Andrew Dunkley here with Fred Watson.
A lifetime of hard work, children laughing in the kitchen, family photos on a restaurant wall, a legacy that lives on. It all comes from the power of a conversation, like the one Tommy Hall had with First Horizon Bank about taking over his father's Charleston-based restaurant business. Now the table is set for a whole new generation. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy. First Horizon Bank, member FDIC.
This episode of Space Nuts is brought to you by LastPass, simplifying your online life. Now, if you're anything like me, you probably find one of your biggest frustrations in life is remembering all your passwords, all those login details, usernames, passwords, important information that have built up over many, many years. And you might have hundreds of them. I know last time I counted, I had like 88 passwords for various things, and it can get quite cumbersome. So what can you do about it? Well, I use LastPass. It's a password manager. It's a fabulous solution to this problem. And believe me, the relief is unbelievable, not to mention time saving. Now, you can sign up for LastPass and you'll be joining 25.6 million fellow users from around the world and 70,000 plus businesses. With those kinds of numbers, they've got to be doing something right. And they do. In my experience, it has simplified everything. I've got every username, every password from everything I do built into LastPass. And it's integrated. I can use it on my desktop, I can use it on my laptop, I can use it on my phone, I can use it on my iPad. It's that simple. And it can even work in a way whereby you don't have to type in anything. You open LastPass, you type in what you're looking for, let's say it's your Gmail account or something, and it will bring it up and you just click on the link and it will open it for you. You don't have to do anything. It is really, really good. Now, you can get the premium package for around $4.50 a month, and there's a family and enterprise plan as well, and it works, as I said, across all devices. Put your passwords in, you can go into autopilot, you can reduce the stress. It's really fabulous. I highly recommend it, and it will give you peace of mind. You will never have to sit there going, oh no, I've forgotten my password. It's one of the worst feelings in the world, and this is the solution. It's really simple and highly secure. I mean, it is very safe. All you have to remember is a master password, one password, so that you don't have to remember any of the others. So check it out. Go to spacenutspodcast.com/LastPass and help support the show. Sign up and you can check it out for free at spacenutspodcast.com/LastPass and just simplify your life. Link details are in the show notes and on our website. Now, back to Space Nuts.
Space Nuts.
Thanks for joining us on the Space Nuts podcast. Andrew Dunkley with Fred Watson. And thank you to our patrons. We're going to hear from a patron soon who's sent us in a question. But if you would like to become a patron, you can do that as easily as jumping on our website, spacenutspodcast.com, and clicking on the link at the top of the page which says support Space Nuts, so strangely enough. Now, you could do that through Patreon, you can do that through Supercast, or you can do it through PayPal, whatever suits you. It's not mandatory. We never will tell you that that's the only way you're going to hear us. It'll always be free to people who don't want to be patrons, and we respect that, and that's fine. But what we are aiming to do long term is basically sever our reliance on advertising. And we take advertising at the moment, but we would like to get to a situation where Space Nuts is 100% supported by the listeners, and that can be done through becoming a patron. So if you'd like to look into that, it would, and you can choose how much you want to pay. It's not going to cost you megabucks. You can go for as little as $3 a month. Which is not a heck of a lot in this day and age for most people, but it's up to you. So jump on our website, spacenutspodcast.com, click on the supporter link and choose your poison, basically, and we'll be greatly appreciative of your support of Space Nuts in whatever form. Now, Fred, let's talk about slabs. Now, I know slabs very well because I've built a couple of houses, and having mortgages, I know that they are supermassive black holes, but these are very different kinds of slabs. We are talking about stupendously large black holes. That's their actual designation, stupendously large black holes, otherwise known as SLABS. I'm assuming we've found a couple?
I don't think we have yet.
Oh, okay. So this is a theory.
It's a theory, yeah. But it's an interesting one. And I might just mention, Andrew, that this kind of directly answers one of the questions that we've had from one of our listeners, Adam, in Newcastle here in Australia, who asks, is there any limit to how big a black hole can get? For example, would it be possible for the supermassive black hole at the centre of Milky Way to absorb everything within the galaxy? I think the answer to that is no, because the black hole itself, even though it's a 4.1 million solar mass black hole, sits at the centre and there is stuff orbiting around it, but it's not kind of roaming around sucking everything in. It just stays put, and stuff that happens to orbit near enough to get within its sphere of influence will be sucked in. But that question relates very much to this news story which has just come out. It comes from the University of London, and in fact has got at least one very big name in it, Professor Bernard Carr, who is an astronomer of my generation. He's somebody who worked in the 70s with Stephen Hawking. So he's got a very strong and well-known connection with the study of black holes. So what's the story? Well, we know, and Adam's question exactly points to this, that most galaxies have a supermassive black hole at their centre. And by supermassive, we mean, masses, anything usually upwards of 1 million times the mass of the Sun, but can be up to 10 billion times, probably some more than that. But there is thought to be an upper limit on these supermassive black holes. We think they grow as galaxies grow, essentially, because the galaxies gobble each other up, and often what that results in is a coming together, an amalgamation of their black holes at their centres, and of course there is also this constant feeding in of gas and newly born stars in the centres of galaxies, which are chewed up by the black hole and make it grow. But the upper limit is thought to exist partly because of the time. To gobble up an entire galaxy would take trillions of years probably, and there just hasn't been time to do that. However, the team led by Bernard Carr have proposed that there might be a population, and you've exactly said what they are, SLABS, which are thought to be even bigger, stupendously large black holes is the meaning of the acronym, but that they were formed at the same time as the Big Bang. In other words, they're not something that's grown in the middle of a galaxy. The suggestion, to use the technical term, it means these things are primordial. They formed when the universe was in its infancy, well before the formation of galaxies. So as these objects are produced in the aftermath of the Big Bang, they don't form from a collapsing star. They form from just the fact that space-time is so distorted by the resonances of the Big Bang, that you may well get a very, very wide range of masses, and some could be very small. And in fact, that's one of the things that Stephen Hawking used to talk about, these small primordial black holes that were thought to litter the universe. In fact, that they were produced as a suggestion for what the dark matter might be. Turns out that it can't be for other reasons, but that was an early suggestion. So Bernard Carr's quote, that's the one really that puts the detail on this. He says, we already know that black holes exist over a vast range of masses, with supermassive black holes of 4 million solar masses residing at the centre of our own galaxy. Whilst there isn't currently evidence for the existence of SLABS, the stupendously large ones, it's conceivable that they could exist and that they might also reside outside galaxies in intergalactic space with interesting observational consequences. And I'll go into that in a second. However, surprisingly, the idea of SLABS has been largely neglected until now. We've proposed options for how these SLABS might form and hope that our work will begin to motivate discussions among the community. So the suggestion is that, maybe maybe SLABS are actually a contributor to the dark matter problem, exactly as Stephen and in fact Bernard Carr suggested back in the 70s, that the small ones might be there. The reason why we don't think there are many small black holes throughout the universe is that we don't see their effect in gravitational lensing, which means that as a black hole passes in front of a distant galaxy or a distant object, you would see a change in the light. It's actually one way of detecting planets going around other stars, by watching them line up with a star a long way in the background and seeing that the light is actually amplified by the gravitational lens around the star and the planet. But the black hole issue is one that kind of was resolved in the 1980s and 90s, that we don't see enough of these gravitational lenses for there to be billions and billions of these small black holes. But the SLABS, the stupendously large ones, might actually make a contribution. You know, if we're talking about trillions of solar masses, the effect of, you wouldn't need all that many to make a contribution to the dark matter situation. We haven't seen any kind of gravitational lensing effects or events excuse me, in the universe that might have been caused by a SLAB. That's the real issue with this, that nobody's observed anything that might be the result of a stupendously large black hole. But it's an interesting conjecture. And what Bernard Carr winds up saying is that the SLABs themselves could not provide the dark matter. But if they exist at all, it would have important implications for the early universe and would make it plausible that lighter primordial black holes might do so. In other words, that we might have got it wrong with the smaller black holes. So it's a bit of a, in some ways, it's putting out a rather controversial suggestion to see what the astronomical community makes of it. That just maybe there are these gigantic black holes wandering around out there, and we maybe should be tuning our search programs, our surveys, in order to try and find them.
It sounds a bit like we're using a theory to try and prove a mystery. So we are theorising that these SLABs exist and may contribute to the dark matter question. So we know about dark matter, not much. We know it exists. But we don't know why. But it could be something that we haven't even proven that exists yet.
Well, that's right. That's the, you know, and that's the great thing about these cosmological studies. You can poke all kinds of ideas out there and see what the community makes of it. So, you know, maybe one day, not far down the track, you and I will be talking about a trillion solar mass black hole that's been discovered somewhere. It's mind-boggling to get your head around something that big, a trillion solar masses. It's a staggeringly large, incomprehensible number. It's 5 galaxies worth.
That is huge. That is huge. And yet we haven't seen one, which either means they don't exist or we just haven't found one yet. I suppose that also throws up the question: where do we look? I mean, where do you start looking? That's the hard part. Yeah.
Probably not towards the middle of our own galaxy, because we know about that one. It's the sort of thing that might big, turn
we'd
up.
Be part of it, wouldn't we?
It's the sort of thing that might turn up in the distant universe.
Yeah, and it can stay there. That would be fine with me.
That's right. That'll be okay.
All right. We'll put a tick on that one, but hopefully in the not too distant future there'll be more to tell on stupendously large black holes. Gotta love the way they name things in astronomy. They don't mince words, really. SLABs. You're listening to Space Nuts. Andrew Dunkley here with Professor Fred Watson.
This is Marshall Rabel with Hubbard Peanut Company. Give the gift of crunchy goodness this year with Hub's Peanuts. For over 70 years, our family-owned company has been cooking and packaging the finest Virginia peanuts in beautiful gift tins, perfect for your friends, employees, or clients. Choose from plain salted or chocolate-covered peanuts. Hub's Peanuts are the perfect way to say thank you, and with our ability to handle large orders, Hubs has you covered. Visit hubspeanuts.com to place your order. Hubbard Peanut Company, Virginia's finest.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
This is Space Nuts, the podcast with Andrew Dunkley and Fred Watson, and you can listen to the podcast on just about any podcast platform. Too long to mention. We're also on YouTube if you want to torture yourself and look at our ugly mugs. That's an option. But you search for Space Nuts podcast on YouTube, and you can watch the vodcast as well. While we're talking about that, let's send out a special thank you and hello to our social media supporters, whatever platform you chase us up on. The Space Nuts podcast group is one that I highly recommend. That's actually not one we created. It was created by the Space Nuts audience. So your chance to join like-minded people and talk astronomy with each other. And from time to time all the time, there are some great topics that are brought up by people who all kind of get into the conversation about this, that, or the other. So, Space Nuts Podcast Group is what it's called. You'll find it on Facebook. Okay, Fred, we've got some questions from the audience, and our first question comes from a very young listener, and we're always very pleased to have young people join us on Space Nuts. This is Ashlyn from Atlanta, who I think has at least 4 questions for us. So we'll see if we can unravel those on this edition.
Hi, my name is Ashlyn. I'm from Atlanta, Georgia, and I got 3 questions. What happens if 2 supermassive black holes collide? And is it possible that there is, like in the multiverses, is it possible there are different Earths across the multiverse? And what is your favorite planet in the solar system and why? And what is your favorite thing about space?
Okay, Ashlyn, thank you for the questions. Fred's going to answer all of those. No, I think we've already been talking about black holes, and that's great. And I think we have talked before about black holes colliding, but in light of the fact that we haven't yet discovered a SLAB, we do know there are supermassive black holes. If 2 of those collided, what might happen?
You get a super duper massive black hole. So we
go.
do know, and this has been observed now with the LIGO gravitational wave detector and the Virgo detector in Italy, that black holes do merge and they combine to produce a black hole whose mass is usually a little bit less than the sum of the 2 component black holes, because there's some of that mass is turned into energy. Thanks to E equals mc squared, and that energy is radiated out as gravitational waves, and that's how we've been able to detect them. And I think it's fair to say that the same would happen with supermassive black holes colliding, and we know that does happen because galaxies are in collision. There are many situations when we look deep into the universe where we see galaxies colliding. Now, this is a process that might take 10 million years or so to complete, but we know that at the end of that process, there is a galaxy with an even bigger black hole at the middle. And usually that galaxy is what we call an elliptical galaxy. It's one that doesn't have spiral arms, because spiral arms are all about the gas that's there. And the gas may well have all been used up but by the end of one of these collisions, because it's triggered star formation. So the odds are, yes, that we will get just bigger black holes when supermassive black holes collide. Just moving on, though, there's some interesting questions. I heard that as Ashlyn. Andrew, you heard it as Ashton. So one of us might be right.
The voice-to-text technology called him Ashlyn as well. So, yeah, my apologies if I got your name wrong.
And mine too. Moving on, the next question was about the multiverses. And once again, we're in an area And it's a bit like the SLABS. This is something that has been sort of proposed from a theoretical point of view. People have proposed that maybe there is more than one universe. And one of the reasons for that actually comes from work that was done a long time ago by the Astronomer Royal in the United Kingdom, who postulated that because the physical constants in our universe appear so finely tuned for stars to exist and planets to exist and life to exist, why should that be? Why should we exist in a universe where all these physical constants are finely tuned? Martin Rees, the Astronomer Royal, postulated that there might be many, many other universes where these physical constants aren't finely tuned. And so you don't get stars, you don't get planets, you don't get people who can talk on space nuts and things like that. So that's where the idea kind of came from. However, we've really got no physical evidence for the existence of multiverses at present. It's merely a theory and a speculation. There are some people who believe passionately about it. Roger Penrose, who got a Nobel Prize last year, he's one of the believers in multiple universes. It's belief's the wrong word because astronomy is not really based on belief. It's based on what we can observe, and so it's more of a speculation than a belief. But if there was a multiverse, or if there are multiverses, yeah, maybe there are Earth-like planets in them. Maybe there are alternative worlds with alternative Andrews and Freds and Ashlyns or Ashtons listening in and doing all the things that we all do. We just have no idea at the moment. It's not impossible.
I suppose in astronomy, you never say never. I seriously doubt that our universe would be duplicated in another universe. I would expect if you could prove the existence of multiverses, they would all be unique. But
yes,
I'd never say never to another universe like ours existing, as in the combinations of stars and galaxies and planets and black holes and slabs existing in a separate universe, but just not the same as us. I imagine that's the most likely scenario. But universes existing that have nothing in them is also, as you said, quite possible. Everything we know is challengeable until we can prove otherwise, or prove that what we're thinking is true, as with stupendously large black holes. So
you've written about all this stuff in your books. So
multiverses, in my first science fiction novel, Parallax. We crossed that threshold. Have a little bit of fun with that. With it. Yeah, yes, it's all done. Yeah, all done. Yeah. He asks about our favourite planets. I can easily go first because I've mentioned it many times. Most people already know. But I love Mars. Why do I love Mars? I don't know. I think I love the beauty of the planet as it's been photographed. If you believe in astrology, it's my ruling planet. I don't believe in astrology, but if you do, that's my ruling planet. I don't know. I think because it's the most Earth-like of the planets in our solar system. There's so many similarities between the two. And I often jokingly say Mars was God's attempt to create an Earth, but he messed it up. So he gave up on that one, and then we came along. Who knows? But I just adore Mars. I just think it's an astonishing planet. If I had a choice to go to any planet anywhere, that would be the one for me.
Well, you never know. You might make it, Andrew, one day.
Very much
Seems
doubt
a bit
it.
unlikely, but you might. So my favourite planet for living on is the Earth, because everything else is rubbish compared with the Earth, even Mars. Yeah. But my favourite planet to look at through a telescope is Saturn. With the ring system. And it's really a favourite planet in many ways because it's such an extraordinarily interesting place with not only the rings, but this system of moons, several of which are possible locations for living organisms. Titan and Enceladus in particular are very high on the list of targets for people wanting to find out further whether there is life in the universe. So, yeah, Saturn, I guess, is my favourite planet, as distinct from the Earth.
Okay. And what's your favourite thing about space, Fred? That's a really tough one for an astronomer, I reckon.
Yeah, actually, I guess my favourite thing is that we can explore it, we can investigate it, and we can understand it in terms of the physics that we know works here on Earth. We can see how many of the mechanisms of the universe work. We certainly don't know everything, and I think there are some areas in which we're really only scratching the surface. But just the fact that we can understand it, I think, is an extraordinary thing about space, especially when you look back, a few thousand years when our forebears were looking at the sky and had no idea what they were looking at when they saw the stars. Just no idea at all.
Yeah, I think for me it's not dissimilar. But the vast unknown is what I like about space. To get really deep and meaningful about it, the existence of existence is the greatest mystery of all. That's what I love about space. How is it here? I mean, as against why? I mean, how did it eventuate? How did it happen in the first place? How is it that we exist at all? That's the big mystery for me, and I that's what I love about space. Is we're piecing it together bit by bit by bit over time. Will we ever know the complete answer? I don't know. If we solve that one, we'll probably be able to solve every problem that's ever existed in mathematics and physics and science and probably not religion, but who knows? Maybe that too. That's what I adore about space. Yeah, fascinating. And thank you, Ashton or Ashlyn from Atlanta, Georgia, for your questions. Very insightful and great to hear from you. And I hope we hear from you again soon. Now we're going to go to, who is it? It's Jarrod in Melbourne, who's sort of following up something we talked about not so long ago, except that I've now managed to lose the question, but I'll find it rather quickly.
Hi, Fred and Andrew. Jarrod from Melbourne here. I know I'm a month late with the E=mc² 100th anniversary, but I had a question about it. Some people will be familiar with nuclear reactions where matter gets exchanged into energy, being released as waves. But I was wondering if Fred could give any examples where the opposite happens, where energy coalesces into matter. And second part of the question, when that happens, why does the energy lose its capacity to travel at the speed of light? Becomes stuck at some slower speed. Thanks both. I'm a patron. I know I get a little kick when PayPal tells me the donation's gone out for the month, so glad to be able to participate. Keep up the good work.
Thank you, Jarrod, for your questions, and thank you for being a patron. You are appreciated, and it is wonderful that you think we are worthy. And if we talked about patrons earlier, and hoping to make the whole podcast patron only funded, so that we don't need to draw on advertising. But we greatly appreciate your support of the Space Nuts podcast. So, yes, what did he ask us?
Well, that's all right. No, I can happily deal with the first part. Can you, E=mc² relates mass to energy, and we know the idea, we're very familiar with the idea of mass turning into energy, because it's what's happening in the sun all the time as the nuclear reactions take place and basically generate energy from the reactions that convert hydrogen into helium. And it also is what happens in nuclear reactors too. You're getting energy out of in a sense, the destruction of mass. And it's because that the factor of the speed of light squared comes into this equation, that you get so much energy out of so little mass. That's the bottom line. So Jarrod's question is, can you do it the other way? And are there any examples? That's a more, that's perhaps a better way of putting it. I'm wondering, Fred could give any examples where the opposite happens. I can give you examples, but it's not the kind of thing that you can do. You can't sort of, set up an experiment in your physics lab or your kitchen or wherever you do your experiments and take a lot of light, for example, and turn it into mass. The best example is the birth of the universe, because at the start of the universe, immediately after the Big Bang, we simply had a universe that was full of energy. And so the energy of that early universe, just because there was so much, the temperature so high, there's so much energy involved with it, that allowed reactions to take place that create matter, and the evidence of that is all around us. So energy was going into mass in the early universe. That's something that it's hard to repeat, just because of the situations. The situation in the early universe was extraordinary. But there are reactions that can be carried out at places like CERN, the European Centre for Nuclear Research, at the Brookhaven National Laboratory there, and in the United States, and Fermilab also in the United States. There is a reaction that you can carry out with a high energy particle accelerator. And what you do is you fire a photon into a heavy atomic nucleus, and I'm not sure what atoms they use for that, but they're hefty ones. Probably things like, could even be uranium, it's stuff like that, or it might be lead. But what happens is there is a reaction takes place, and in fact the nucleus of the atom sort of shares the energy around, and the photon disintegrates into an electron and a positron. So a positron is the antimatter opposite of an electron. It's got the opposite electrical charge. That positron then collides with an electron and turns back into a photon. So it's a very temporary creation of mass, but it does happen. So yes, that is true. We can manufacture matter from light, but we can't make it last very long. And we certainly can't create something out of nothing, which is a very nice way of putting it, courtesy of the How Stuff Works website. It's worth having a look at that.
Yes, indeed. That said, people will still continue to turn lead into gold, I'm sure.
Yes, that's right. That was what it all came from, I guess, in the early days.
Yes. Now, he does also ask about energy losing its capacity to travel at the speed of light and becomes stuck at slower speeds. Would that be simply because space is not a vacuum, an absolute vacuum?
Yes. Well, that's one reason why light travels at a slower speed. For example, if it goes into glass or water, its speed slows down very considerably, and that's how refraction takes place. But light does lose energy in the vacuum of space, but it doesn't slow down. What happens is it gets redshifted. Its energy. So blue light is high energy light, red light is low energy light. Loss of energy equates to a change in the in the color of the light. There was a time when, and this is going back probably about 40 years, I remember being involved a little bit with some of these speculations, that the effect of redshift that we see when we look out into the universe might be something that's causing the universe to sap the energy of the photons. And so the redshift is not telling you that the universe is expanding, but just that the light is getting tired. In fact, tired light was the name of the work that was done with that. But it simply didn't hold water. The only plausible explanation for why we see redshifts all over the sky is that the universe is expanding, which is another way of losing energy. The space is stretching. So I hope that answers the question. Thank you very much for being a patron, Jarrod, and thanks for your questions too.
Indeed. Thanks, Jarrod. Thanks, Ashlyn. And thanks to everybody. We've got a whole batch of new questions, so we'll work our way through those. But a reminder again, if you do have a question, you can go to our website and upload it as text, or you can go to the AMA tab and record it with your voice. Just don't forget to tell us who you are and where you're from, because we like to know. If you don't want to, that's fine, but it gives you an opportunity to voice your question through to us, and we'd love that. But whatever format you want to send your questions into us, that's fine too. It's all there on the spacenutspodcast.com website. That brings us to the end of another episode. Fred, thank you so much. It's always a pleasure, as I say, and greatly appreciated.
Yeah, thanks, Andrew. I appreciate being able to talk to you as well. It's always good fun. And we'll see you soon.
It is. Yes, we will. Catch you in about a week or so. That's Professor Fred Watson, astronomer at large, part of the team here at the Space Nuts podcast. And from me, Andrew Dunkley, thank you for listening, and we'll talk to you again real soon. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.